Hello everyone, and welcome to this video on simplifying expressions involving rational exponents. Alright, when I say the word rational, you should be thinking of fractions. Alright, so a ratio of two integers. So we're looking here at expressions where there are exponents that are fractions, and asked to simplify those using properties of exponents, which I'll get to as we go through the examples. I'll demonstrate what property I'll be using for the example I'll be using it for, right, as we go along. Alright, so in this video, all my examples today, when it says to simplify, right, and if in the following examples, simplify will mean to do the following. Alright, I'm going to rewrite the expression so that we have all positive exponents, right? All exponents are positive, so no negative powers when I'm done. Number two, each base, right? Remember there's a base and an exponent, right? The number being raised to the power is called the base. Each base occurs only once, right? So I'm not going to have an x squared in one part and an x to the third in another part, right? We're going to put those together, get every base occurring only one time. And lastly, there are no powers written to powers. Alright, so I'm not going to see x to the second and then that again raised to the third power. So no power to any power. Right, power to power. Alright, so let's keep these in mind, and I'll reiterate those as we go through my examples. And I'll check them off as we go through just to make sure I've completely simplified my expression. And of course, if I know the value of a number, I'm going to say what that value is, right? If my example has all numbers in it. All right. So my first example is the following. All right. Where I say simplify each expression, and this is going to be the direction for everything. And then this instruction here, you see this quite often in texts. Assume all variables are positive. So if you recall from a previous video on roots, on radicals, remember how the square root of, say, a squared, the square root of a perfect square, or really just any even root, right? Remember when we took any even root, right? Or the nth root of a perfect nth power, where n was even. Recall that wasn't just a itself, but the absolute value of a, because this base here could be a negative number, and whenever you see this symbol with an even root, the result needs to be non-negative. You're being asked for the non-negative nth root. So it's not just a, but the absolute value of a. But if they're saying assume all variables are positive, right? If we assume a is positive, if we assume all the variables are positive, well then we don't need the absolute value symbols, right? Because a is already a non-negative number. So if you ever see this instruction when you're asked to simplify an expression involving radicals, or remember radicals are just like these roots, right? These fractions. Anytime you see a fraction power, you're dealing with radicals. Showed that as well in the last couple videos, the relationship between those. So if we assume that all the variables are positive, we don't need the absolute value symbols to ensure that our result is non-negative. So just keep that in mind if you ever see that instruction. You don't need the absolute value. Now if this instruction isn't there, right, if you're ever asked to just assume, if you're ever asked to just simplify an expression and they don't tell you, hey, all the variables should be a positive number, then you need to ensure that your even roots end up being non-negative by using absolute value symbols. Right? But I'm not going to do that here. Right? We're not using absolute value symbols today. because we are assuming all the variables represent positive numbers. Okay, so enough of that. Now let's talk about the property I plan on using. Alright, so here I have 5 to the 3/4 power multiplied by 5 to the 1/6 power. So you see it's not considered simplified because, number 2 is off, right? Each base only occurs once. Well, here I have a base of 5, right? Exponent 3/4. And here I have the base of 5 exponent 1/6. So you have two parts of this, two factors of this product here where the base is 5. So this number 2 is not happening, right? I have a base occurring more than once. All right, so the property of exponents that's going to come into play for this example and in future examples is sometimes referred to as a product property. I'm just going to write it out. If you have, say, some number a, I'll use capital A, raised to the, say, mth power, right? So here's a to the mth power, and it's multiplied by, and then the same base, right? So base a exponent m, base a exponent, say this exponent is n. You can simplify this. You can write it to where you have a single base and not two of the same base. As keep the base, and then the new exponent is the sum of the previous exponents. So a to the mth multiplied by a to the nth, same base, keep the base a, add the exponents, the new exponents m plus n. Alright, so this property I'm going to employ for this example. Alright, and I'll rewrite that down here. So we have 5 to the 3/4 power times 5 to the 1/6 power. Right, so you see the 5 is like the a, the 3/4 is like the m, the 1/6 is like the n. So I'm multiplying two things with the same base, keep that base, and then the new exponent is the sum of the previous two. So the new power is 3/4 plus 1/6. And write it really tiny, make sure that's all in the exponent, and so I have a base of 5 and then an exponent of 3/4 plus 1/6. Now we can again further, when we say simplify, it still applies to all the numbers we're used to adding and subtracting. Adding fractions, we can simplify those by putting those together. So off to the side here, let's look at that exponent. All right, the exponent is 3/4 plus 1/6. I can put these together, but not right now. Remember, when you add or subtract fractions, like I'm doing here, you need a common denominator. Right? You need the denominators to be the same. So you need to find the least common denominator, or least common multiple of the denominators. Right? So that would be what? The LCD here, least common denominator. The least common multiple of 4 and 6 would be 12. So what would need to be done? I'd multiply this first fraction by 3 in the numerator and 3 in the denominator to give me a denominator of 12. And don't forget, what you multiply the denominator by, you must also multiply the numerator by, so that way it's like you're multiplying by 1 and not actually changing the value of the number. Same thing for the 1/6. I want the denominator to become 12. I multiply the denominator by 2. 6 times 2 is 12. But I must also then multiply the numerator by 2. Right? That way it's, again, I'm like multiplying by 1 and not changing the actual value of 1/6. Right, so now this first fraction is 9/12, right? 3 times 3 over 3 times 4, 9/12 plus, then 1 times 2 over 2 times 6, it's 2/12. And 9/12 plus 2/12, when you finally get that common denominator and you're adding, that common denominator stays, right? 12, 12, 12 here. You're just adding or combining the numerators. 9 plus 12 is 11. So this is the exponent, right? 3/4 plus 1/6 is 11/12 when you combine that to be a single number. So our final result here is 5 to the 11/12 power. And then you might ask, well, what is this? Right, I'm going to put this in a box right now because this has everything I want. Notice going back to the simplify page here, all the exponents are positive, right? The only exponent here is 11/12, and that is positive. Each base only occurs once, right? The base of 5, I'm not seeing any other part of this expression with another base of 5, so every base occurs only once. And there are no powers written to powers, so you're not seeing 5 to the 11/12 and then that in parentheses again to the third power or something. There's not a power to another power here. Also, I don't really know what this is, what the exact value of this is. Because remember from last video when I was evaluating numbers to fraction powers like this, what we would be doing here is taking the 12th root. Remember the denominator tells you the index of the radical if you change it to a radical. You'd be taking the 12th root of 5, which I don't know, right? 5 is not a perfect 12th power. The 12th root of 5 and then that 12th root of 5 to the 11th power afterwards. And let me show you, this is not a nice number, a nice rational number. Let me show you what 5 raised to the 11/12 power is some crazy decimal, 4.372426361. It's one of those irrational numbers where the decimal would go on forever without ending or having a repeating pattern. So this is where I would stop. I can't write this as a nice simpler rational number. 5 to the 11/12 power is as simple as this expression will get for me. Okay. All right, my next example is again similar, and I'm going to again put up a nice property of exponents that we're going to be using. And don't forget this one. This one will come back later as well. When you multiply two things with the same base, you keep the base, add the exponents. All right, the next one, same instructions. All right, I'm asked to simplify the expression and assume all variables are positive. Well, there's no variables here. All right, there's just numbers. All right, so in this example, the property of exponents that I'm going to be employing is the following. You might call this the quotient rule or fraction rule. But if I take a number, say a again, raised to the mth power, and now this time you see there's division, there's a fraction, divided by, and then that same number, notice it's the same base twice, right? So number 2 is off, right? When each base occurs only once, that's not happening here. I've got a base of 32 on this exponent, and then a base of 32 again on this exponent. So I have a to the mth divided by, and then the same base to say the nth power again. All right, now when you divide two numbers with the same base, keep the base just like when you multiplied. But the exponent this time is the numerator exponent minus the denominator exponent in that order, m minus n power. All right. So here in this example, the a throughout this is the number 32. My m, the numerator exponent, is 6/5, that fraction, and my n, the denominator exponent, is the 3/5. All right, so in dividing these, 32 to the 6/5 power divided by 32 to the 3/5 power, I keep the base, right? So the base of 32, and then the exponent is the numerator exponent minus the denominator exponent. So to the 32 is the base, and the exponent is 6/5 minus 3/5. Okay. And then, of course, like the last example, I can simplify this. We know what 6/5 minus 3/5 is. So the base is 32. And these already have the same denominator, right? I don't have to change denominators like I did in the last example. So the denominator is going to be 5 for the exponent, and the numerator is just combine the numerators. 6 minus 3 is 3. Okay, and this is great, right? All exponents are positive, right? I have 32 to the 3/5 power. That's a positive exponent. Each base occurs only once. 32 occurs only once. Right? There's no other, it's not like two of them over here. There are no powers written to powers, so I'm not seeing that either. 32 to the 3/5 is, that's not in parentheses being raised to some other power. So this is great. All right, this is kind of what they want, but I'm recognizing here my denominator is 5, meaning I'm taking a 5th root of 32 and then raising that to the 3rd power afterwards. Let me write that out. Now in the last example, when I was doing the 12th root of 5, I don't know the 12th root of 5, but this one actually is a number I do know, a nice rational number. 32 is actually a perfect 5th power. What you have here, and again, you go back to my last video, you can write this as a radical, as the 5th root of 32, and then raise that to the 3rd power on the outside here. And what is the 5th root of 32? What number to the 5th power would be 32? That's 2. All right, so inside the parentheses there, that's the number 2. 2 to the 5th power would be 32. And then you cube it, right? Then you raise it to that numerator of the power of the 3rd. 2 to the 3rd is 8. So this is even more simplified. Right? Just the plain old number 8. All right? 8 to the 1st, if you want to write 8 to the 1st power, 8 to the 1. But this is good. But because I know the 5th root of 32, we can continue on, and this is even better, even simpler. If you want to double check, let me punch that in. Here's 32 raised to the 3/5 power, and we're seeing 8 there. I know it's kind of glary on my video, but the number 8 does come back. Wonderful. All right, so again, another property to keep in mind. This will come back later as well. When you divide, or when you have a factor in the numerator and a factor in the denominator with the same base, you keep that base and subtract the exponents. Numerator exponent minus denominator exponent. Great. All right, my next example is going to employ another property of exponents. So here I have, in parentheses, 100 to the 3/8 power. Right? So base 100, exponent 3/8, but then that's in parentheses. So that becomes the base. This whole thing is the base on the exponent of 4/3. So I have 100 raised to the 3/8 power, and then that is also raised afterwards to the 4/3 power. So this is that power to a power, powers written to powers that I was talking about. So number 3 is failing here, right? There is a power written to another power. So how are we going to simplify this? All right, so another property of exponents that you should know. This is a power to power property, power written to power. If you have a number, you can say a, and that's raised to an exponent, say m, and then you take that number and make it the base and raise that base to another power, say n. Well, then you keep the original base, the a, as the new base, and then the exponent on a is the product. You multiply these as the product of these exponents that are written in the power to power form. So the new exponent is m times n, or mn, right? That's m times n. All right, so in my example here, the capital A is the 100, the 3/8 is the m, and the 4/3 is the n, if you want to just replace those. But all right, so what do we got? So 100 to the 3/8 to the 4/3. Well, that's a power to a power, so that'll be equal to the original base, the 100, raised to a new power. And that new power is going to be 3/8 times, right? The dot for times, multiplication, 4/3. All right. And what I'll do this off to the side. Here's the exponent. It is 3/8 times 4/3. Now you may have done this before, multiplying fractions. I'm sure you have, right? You can do some cancellations now. If you notice there's a common factor in the numerator and denominator, 3 and 3 divide out to be 1, 4 divided by 8 is 1/2. This ends up being just 1/2. Right? Or you can follow through the long way. It still ends up being the same. When you multiply fractions, right, you don't need a common denominator. You don't. That's only for adding and subtracting. When you multiply fractions, you simply multiply the numerators. 3 times 4, the new numerator is 12. And multiply the denominators. 8 times 3 is 24. And then simplify by dividing out common factors. 12 is 12 times 1. 24 is 12 times 2. And then you have this common factor of 12. And as I said earlier, you can cancel earlier if you want, but you end up with a half when that's totally simplified, when the numerator and denominator don't have any common factors anymore. Okay, so this 100 to the 3/8 times 4/3 is equal to 100 to the 1/2 power. Now this is great, all right, it satisfies these three, but it's not completely simplified because I know what this number is. Right? All the exponents are positive. The base of 100 only occurs once. There are no powers written to powers anymore, right? It's just a single power, single exponent. But if you recall from last time, right, a couple videos ago, last couple videos, when you take a number and raise it to the 1/2, right, the denominator is 2, telling you you're taking the square root of that base and then raising it to the first power. There's no need to raise to the first power, it doesn't do anything. But this is the square root of 100, the non-negative square root of 100. So I know -10 squared is 100, -10 times -10, but again, this symbol, when you see the radical symbol, when you see the half power, you're being asked for the non-negative square root. So this is +10. Right? +10. And again, you can go ahead and punch that in. Go to a calculator, put it in 100 raised, little caret button, to the 1/2 power, +10. Okay. Great. So another property that'll keep coming into play. When you have a power raised to another power like that, you multiply them. Right? Keep the original base, multiply them. All right. Now my next example actually brings a couple properties into play. All right. Now we've already seen one of them. It's actually the power to power one that I just had here. But there's another property also to be demonstrated. All right. So here I have, in parentheses, a to the 3/2, a to the 3/2 power, times b to the 5/4, and then all of this in parentheses is raised to the 2/3 power. Okay. So what I have here is a product, right? Product, this is multiplication in here, a product raised to a power. And that brings me to my next property of exponents. When you have a product raised to a power, what you can do with that power, that exponent. So if I have in parentheses, if I have a product, say the number a times the number b, and this product, multiplication, is being raised to the mth power, some exponent. Well then, you can, if you want, this is equivalent to raising each factor to the mth. So a times b in parentheses to the mth is equal to a to the mth power times b to the mth power. So basically you can put the exponent as the exponent on each factor. Right, and this is not distributing, right? This is not called distributing. Please know that. All right, so we're going to combine actually this property with our previous property of raising a power to a power and then multiplying the exponents. Right. So you see here how the capital A is this a to the 3/2 power. The capital B is the lowercase b to the 5/4 power. And then the m is the 2/3 power. Right. All right, so let's go through this. All right, so this is going to be equal to, you take the first factor, the a to the 3/2, and I'll put it in parentheses just because we're raising this to another power. I have a to the 3/2, and then that's being raised to the 2/3. Then times, and then the next factor, this b to the 5/4. That's also being raised to the 2/3 power. All right, so great. I've used this product to a power property, right? Each of these two factors was raised to this 2/3 power. Right? But now I have the case where, like in the last example, I have a power written to another power, right? A to the 3/2 to the 2/3 times, and then b to the 5/4 to the 2/3. Right? Okay. So what do we do then? Remember, you multiply those. Keep that same base a to and then the exponent on this now is 3/2 times 2/3. All right, that's this first factor times the second factor. You have b to the 5/4 to the 2/3. You keep that original base b, and then the new exponent is 5/4 times 2/3, right? All right, and then we simplify. What's 3/2 times 2/3? That'd be 6/6, or 1. So this is a to the 1, or just a. All right. Now remember earlier how we said, in the instructions for these, it was mentioned that we were supposed to simplify and also assume all variables are positive. Look at this, right? See how this started? I had a to the 3/2. The denominator on this was 2, meaning I was going to be taking the square root of a and then cubing it. Well, if you're taking an even root, right, you remember you can't take an even root of a negative number, because that won't be a real number. So even from the get-go, I can show you that a had to be non-negative, and same thing for b, right? B to the 5/4, you'd be taking the 4th root of b and then to the 5th power after, but that even root of a number, that number cannot be negative. So the a and b have to be non-negative, and to ensure that the result is non-negative, we would usually put absolute value around this, but we are told to assume that the variables are positive. So if a is already positive and b is already positive, I don't need to write the absolute value symbols. Normally I would, but I don't have to. Right? Okay. Times, and then the next one, this is 5/4 times 2/3. That'd be 10/12. All right, 5 times 2, 4 times 3. And hopefully you see that 10/12, right? 10 and 12 have a common factor of 2. That would reduce to 5/6, right? So you have a to the first, or just a, times b to the 5/6 power. And this is going to be considered simplified. I'm going to put it in a box. Right, because 1, all the exponents are positive. You have here a to the first exponent of 1, and b to the 5/6, right? That's also a positive exponent. Each base only occurs once, right? There's only one base of a, right, under the first power. There's only one base of b under the 5/6 power. And there are no powers written to powers anymore. Those were up here, right? The 3/2 to the 2/3 and 5/4 to the 2/3. And so this is as simple as it gets. And a and b are again assumed to be positive, so I don't have to worry about do I need absolute value symbols around these or anything like that. Okay, great. All right. So the next one, again, all these properties I've been writing are just going to keep on being used. All right, so this one. Now, you can do a lot of these problems in several ways. There are, because it doesn't matter really what order you perform the properties in a lot of the times. So let me show you for this example anyway, just how you could do it in a couple different ways. And then the following examples, I'm just going to do it one way and just remind you that you can also do it in another way if you see a better one. I'm just going to do it, so this one I'll do in two ways. All right, so let's say this is method 1 over here. So I have x to the 1/2 times x to the 1/3 divided by, that's all the numerator. And then down here I have x to the 1/12 and then to the second. So right away we can, I know we're already told to assume the variables are positive. But look, here I have the x to the 1/2 power, right? That's the square root of x, so x can't be negative from this. And I also have this x in the denominator, so x to this power, this x can't be 0 either. So from this, x has to be non-negative. From down here, x has to be non-zero. Putting those together tells me that x has to be positive. So even without being told x has to be positive, I can see from the expression that the only numbers I could actually plug in for x are positive ones to give me a real number output. All right, so the first way, and this is the way I typically work with fractions, is I simplify, simplify the numerator and denominator separately, and then do the whole thing. So in the numerator, above the big bar here, we have x to the 1/2 times x to the 3rd. Now remember that property earlier. When you multiply two factors with the same base, these both have a base of x, you keep that base, so x again, and then the exponent is the sum of these two, so x to the 1/2 plus 1/3. All right, and we'll simplify that in a second. All right, divided by, and again, I'll just keep doing the numerator. I'm going to simplify the numerator, then the denominator separately, and then we'll look at the whole thing. All right, now 1/2 plus 1/3. You can do this off to the side or whatever. I'm just going to kind of say it out loud. You need a common denominator when you add, right? This is a plus. The least common multiple of 2 and 3 is 6. This I'd multiply by 3 over 3. This fraction I'd multiply by 2 over 2, giving me 3/6 plus 2/6 would be 5/6 when you total them. So in the numerator I have x to the 5/6 power. Okay, so that's the numerator completely simplified. The denominator, I have that power to power, x to the 1/12, and then that again raised to another power of 2. So this would be x, right, keep that original base, to the, and then 1/12 times 2. Now you can also think of 2 as 2 over 1 if you want to think. So this is 2 times 1 divided by 12 times 1. 2 divided by 12, or 1/6 when you reduce that. This would be x to the 1/6 power. Right, so I've simplified the numerator on its own, simplified the denominator on its own, and now look at the whole thing. right? And I have this case just like a property I showed you earlier, that division property. I am dividing two numbers with the same base. So you keep that base, so x to some power, and then the new exponent, right, is the difference in these exponents, the numerator exponent minus the denominator exponent. So 5/6 minus 1/6. And then we simplify that number. Adding and subtracting, need a common denominator, already got it. So the denominator is 6, and the numerator would be 5 minus 1, or 4. So this would be x to the 4/6 power, but 4/6 reduces to 2/3. Right, the 4 and 6 have a common factor of 2. And this, right, this is completely simplified. All right, there's all exponents are positive. Each base, the x only occurs once, and there's no more powers to powers, right, like there was over here with the 1/12 to the second. All right, so this is the way I prefer. I'll write that up here. I prefer doing this with fractions when fractions are involved. You don't have to do that, right? Like I said, there's loads of other ways. Here's another method. Right, so you could say or, method 2, where I'm just going to mess around with this a bit. I'll keep the x to the half times x to the 1/3 up top, and then simplify the denominator, right? Remember, this is x to the 1/6. We already did that. And then I see I can do that division property, right? I see a factor part of a product, right? If this was a plus, I couldn't do this, but I have a multiplication. I see a factor with a base of x in the numerator, and I see another factor with a base of x in the denominator. So I can put these together, make these into a single factor, and then we're going to be multiplying by x to the 1/3. So when I put these together, that'd be x to the 1/2 minus 1/6, then times the x to the 1/3. And what is 1/2 minus 1/6? Well, that would be 3/6 minus 1/6. That'd be 2/6, or 1/3. So this is x to the 1/3 times x to the 1/3. And now I have that case where if you multiply two things with the same base, you keep the base and add the powers, and 1/3 plus 1/3 is 2/3, and I'm getting exactly what I got earlier. All right, so again, you decide, and that's not the only way. I could have divided these two first, and then multiplied by x to the half and got the same thing. Okay, so I'm going to just say this in the rest of the examples, that there are usually many different ways. It depends on what order you decide to use the properties. There are usually many different ways to rewrite an expression, to simplify an expression. All right. But I'm only going to do one way from here on out. The way I see it, the best way I can see it to be done. All right. So my next example. I have in parentheses 8 times x to the 3/4 times y to the -1. All right. And then this is being raised, this whole thing. So this is a product, right? This is multiplication when they're touching like this. There's no pluses or minuses in here. This is being raised to 2/3. All right, so remember that product to a power rule I wrote up earlier? You can take a product that's raised to a power and write it as the product of each factor to that power. So this product to the 2/3 is equal to 8, the first factor to the 2/3, times, and then the next factor in here is this x to the 3/4. I'll put in parentheses because we'll have a power to a power. So there's the next factor, and that's also being raised to the 2/3, times. And then this last factor, and we'll talk about negative powers in a second, right? It said up top, all exponents are positive. We have, y to the negative first, and I'll show you how to rewrite this negative powers as positive powers. And that third factor is also being raised to the 2/3 power. Okay, so now I have a case where we got some powers to powers. And this first number here, this first factor, 8 to the 2/3, I know what that is. All right. Remember, the denominator is 3 on this power. So that's telling me I'm taking the cube root of 8 first and then squaring it, right, raising to the numerator. What is the cube root of 8? It's 2. And then 2 squared is 4. 8 to the 2/3 power is 4. So I've got 4 times, and then here I'm, power to a power, that property. I'd have that base of x to the 3/4 times 2/3 power. We'll simplify that in a second. Times, and then again, power to a power, I multiply those exponents, keep the base of y, and then raise to the -1 times 2/3. All right, so going over here, we got the 4, or 4 over 1 if you want to think of it that way, times x to the, this power, this 3/4 times 2/3, that'd be, 3 times 2 is 6, 4 times 3 is 12, 6/12, which reduces to a half, and then times y, and then, -1 times 2/3 would be -2/3. All right, so I'm almost there, right? Each base does occur only once, right? You got 4 occurring once, x as a base occurring once, y as a base occurring once. There's no more powers to powers. It's just the first one's messed up. All exponents are positive. That is not the case here. So what do we do? All right, so here's another property of exponents dealing with negative powers, negative exponents. And I've put this up in a previous video as well, recently. When you take a number and raise it to a negative power, so say I have a to the -n, let's assume n is positive, so negative n would be negative. This is equal to the reciprocal of the positive power, a to the positive n. So you take a to the positive n and flip it over, making it 1 over a to the positive n. All right, so, and of course, a can't be 0, or you can't divide by 0. Alright, you can have 0 in denominators. Alright, so down here, you see this negative power? See the y to the -2/3? That y is like this a, and the 2/3 is like the n. Alright, so let's go through here. So now we have this. We have factors of 4 times x to the half times, and then just put little dots for times, and then this y to the -2/3 is 1 over y to the positive 2/3. And this is great, but let's put it all together as a single fraction. This is everything we want, right? All the exponents I see are now positive. All the bases occur only once, and there's no powers to powers, but let's just get a single numerator, single denominator. So multiplying the numerators, I have 4 times x to the half times 1. That's just 4 times x to the half in the numerator, divided by, and then in the denominator, right? These two don't have denominators, so technically you can throw them over 1 if you want. 4 over 1, x to the half over 1. And then your denominators is 1 times y to the 2/3. So that y to the 2/3 also in the denominator. And there you go. Right, there's a nice, that is totally simplified. And again, we are assuming here that all variables represent positive numbers, that x is a positive number and y is. Now, y doesn't have to be, right? X does. You see how I have x to the half? That's an even root. So x has to be non-negative. But y, y is raised to the 2/3. I'd be taking the cube root of y. So y can be anything, of course, except 0, because you can't have 0 in a denominator. But let's just, again, we're assuming the variables are positive, so let's not worry too much about that. I'm not going to write that down. Great. All right, and then the last couple, I have two more examples that kind of combine a lot of the properties. All right, and in fact, I even have just one more property to show you. We've seen a product to a power, but we haven't seen a fraction to a power or a quotient to a power, and that's really the last one I've got for you here. So before I get to this, let's just put up the last properties that we haven't seen yet. Right, so I got two of them here for you. One is if you take a fraction. So if I have some number a divided by some number b, some fraction, and raise that to a power, say the mth power or the nth power, whatever. This is equivalent to the numerator to that power, so a to the mth, divided by the denominator to that power. You can put the power on the numerator and denominator separately, and they will be equal. And the only other one I haven't shown you that might come up, I haven't really seen that in any of my examples yet, but if you take any number that's non-zero, and I guess back up here, b shouldn't be 0 because you can't have 0 in denominator. But if you take any non-zero number and raise it to the 0 power, you're going to get the number 1. I know that might sound silly, but go to other I'm not going to go into it here so much, but just go into other videos, look for other videos on the properties of exponents, the 0 property, and you'll get a further explanation of this, I promise you. But for right now, let's just take it for what it's worth. Any non-zero number to the 0 power is going to be equal to 1. All right. Make that look more like a 1. Okay. All right. So this example here, do you see I have a fraction to a power? This 25 times x to the half times y to the 3/4, that is like the a here, the numerator, and this x to the negative 3/4 times y, that whole thing in the denominator, that's the b, and then the half outside is the m. So using that property of a fraction to a power, I'm going to take this entire numerator, right, the a to the mth power, so the whole numerator, so 25 times x to the half times y to the 3/4, that whole thing to the half, divided by, and then the same thing with the denominator to the half, right? So the whole denominator, this x to the negative 3/4 times y to the half. All right, that's using this property here. All right, and now, like I like to do, I'm going to simplify the numerator and denominator on their own, and then we'll do all sorts of division and stuff. In the numerator, above the bar, I can use that product to a power rule. So we have, this is a product, right? There's no addition or subtraction here. So each factor can be raised to the half. So 25 raised to the half times, then x to the half raised to the half, and I put that in parentheses, that's all that factor, and that's raised to the half as well, times, and then the y to the 3/4 raised to the half. All right, this is the numerator. All right. And let me totally simplify that. I'll do that over here. Simplify the numerator first. 25 to the half, I actually know. All right, 25 to the half, that's just the square root of 25. The non-negative square root of 25, that's 5. All right, so that's 5 times, and then I'm going to kind of skip a little ahead here, one step. Remember here I have power to a power. X to the half, and then that again to the 1/2. So I have times x to the 1/2 times 1/2. 1/2 times 1/2 would be 1 times 1 in the numerator, 2 times 2 in the denominator. That'd be to the 1/4 power. Okay. Times, and then you have y, and then again power to a power. Y to the 3/4 to the half, so you keep that base of y. And then 3/4 times 4/2, that'd be 3 times 1 in the numerator, 4 times 2 in the denominator, 3/8. Y to the 3/8 power. All right, so there's the numerator totally simplified. 5 times x to the 1/4 times y to the 3/8. And then I do the same to the denominator. So again you see this product. I have x to the negative 3/4 times y, a product to a power. I can put that power on each factor. So you have this x to the negative 3/4 raised to the half times, and then just y, the other factor, raised to the half. Okay. Here we have power to a power, x to the negative 3/4 to the half. So I keep that base of x, and then negative 3/4 times a half would be negative 3/8. Negative 3/8. So we have x to the negative 3/8, and then times y to the half. All right. So it's almost done. Almost done. Got a couple things that are wrong here that not simplified. First off, all the exponents are positive. No, they're not. There's an exponent of negative 3/8 on this base of x. Each base occurs only once. No, they don't. Here's a base of x. Here's another base of x. Here's a base of y. Here's another base of y. Right. So numbers 1 and 2 are failing, and there's no powers written to powers. Well, that's okay. There are no powers to powers here. All right. So what I'm going to do is like earlier, use that division property. So I got this is 5 over 1. You see I have these two bases of x that are these two factors. There's a factor in the numerator with a base of x, and a factor in the denominator with a base of x. And remember what happens when you have a factor in the numerator and a factor in the denominator with the same base. You keep that base and subtract the powers. And then you'll be multiplying also by, I've got the same thing happening here with the y's, right? There is a factor in the numerator with a base of y, a factor in the denominator also with a base of y. So I'm going to use that division property we saw earlier. All right. So this is equal to, well, I've got the factor of 5, 5 over 1, 5, right? There's 5 times, then when I divide these two out, you have that base of x to the 1/4 minus, so the numerator power minus the denominator power. So this is where it might get a little tricky. It's the numerator exponent, remember, minus the denominator exponent. So minus negative 3/8. So you have minus a negative here, which will end up being a plus. And then times, and then you have to do the same thing with the y's. I have a factor in the numerator and denominator with the same base of y. So you keep that base, a times, you keep that base of y, and then subtract the exponents for the new exponent, 3/8 minus 1/2, right? Numerator power minus denominator power. All right, so let's go here. We got the factor of 5, and this you have x to the. This is, remember, this is 1/4 plus 3/8. This is 1/4 plus 3/8. You need a common denominator, which would be 8. So this is 2/8 plus 3/8. That'd be 5/8. Positive 5/8 for the power on x. X to the 5/8 times y to the, and then again you need a common denominator when you add or subtract. This is 3/8 minus 4/8. Right, 1/2 is 4/8. 3/8 minus 4/8 would be negative 1/8. So almost there, almost there. Every base is only occurring once now, but I do have a negative power. And now I'm just going to employ, remember that this happened in an example or two ago. When you see a base with a negative power, this is just the reciprocal, right, of the positive power. So we have 5 times x to the 5/8 times, and then this y to the negative 1/8, is the same as 1 divided by y to the positive 1/8. And so really all that does is put y to the 1/8 in the denominator. Right? You multiply these numerators, you got 5 times x to the 5/8 power divided by, and then multiply the denominators, you have y to the 1/8 power. And that's it. This would be considered simplified by all my criteria. Right? All exponents are positive. Every base occurs only once, and also there's no powers raised to powers. No powers written to powers. Okay, and now I have one final example for you, where I'm again employing several properties in the same example. And again, there are other ways to do these. You don't have to do these in the exact same order that I am. It's just the way I'm seeing to do it right off the get-go. Right. So my last example, same thing. I'm asked to do these three things. Simplify, assuming all the variables are positive, so that means I don't have to put absolute values around anything when I'm done, just to ensure that anything's non-negative. Alright, so here I've got this factor of 8. That is outside. That is not part of the base, right? This is the base on that power of 2/3. Right, that 125 times a to the 3/4 times b to the -1, that's the base. So the 8 out front, that is not part of the base. So that's just going to stay the factor of 8 the whole time. So I'll have 8 times, and what I see here is again this product, right? This is one big multiplication problem here inside the parentheses. 125 times a to the 3/4 times b to the -1. I'm going to use that product to a power rule. Alright, so times, we got 125 raised to the 2/3 times, and then this factor of a to the 3/4, and I'm going to have a power to a power, so I'll put parentheses, a to the 3/4 to the 2/3 times, and then again I'll have a power to a power, this last factor, b to the -1 to the 2/3. Alright. Okay, so then writing these out, this is a factor of 8 still, that doesn't go anywhere, still 8, 8, 8 times, now 125 to the 2/3, I know. What's the cube root? Right, the denominator tells you the root, right? Take the cube root of 125, which would be 5, and then square it. So that's 25. Right? 125 to the 2/3 power would be 25. Times, and then here we have a to the, and I'm just going to multiply them now, a to the 3/4 to the 2/3, that's power to a power. You'd multiply these exponents. 3 times 2 in the numerator, 6, 4 times 3 in the denominator is 12, 6/12 reduces to 1/2. So I just have a to the half. And then finally times, and then b to the -2/3, right, -1 times 2/3 power. Alright, and hopefully you can see, 8 times 25 is 200. Simplify that. Times I have a to the positive half. Alright, a to the positive half power. And this b, just like earlier past two examples, this b to the -2/3, I can write as 1 over 1 divided by b to the positive 2/3. So all that's going to do is slide b to the positive 2/3 into the denominator, and here we have it. That's the simplified version of my expression up here. All right. And with all of these, with the variables, like this one's with a's and b's, if you want to test it out, replace the variables with some numbers and see if they're actually equal. Punch them in your calculator or something. And again, just assuming that variables are positive, so punch in replace a with 3, right, and b with 7. I don't know, right? So let me show you that with just this one example here. So let's say a were equal to 3, so I'm going to let a be 3 and b be 7, and I'm going to punch these two in my calculator. So up here, the original expression, 8 times, and then in parentheses, 125 times, and I'm letting a be 3, right? So 3 to the 3/4 power, 3 to the 3/4 power. then times, and then b to the negative 1. So 7 to the negative 1. All right, then I close parentheses, and that gets raised to the 2/3 power. All right, we get some crazy number here, 94.6655428.6 and so on. Well, I'm going to keep that up. I'm going to keep that up there. And let's go down to our expression down here and punch in 3 for A and 7 for B and see if we get the same number. We better, right? If this is truly equal to this, and again, you can do this with other examples I had with variables in it, replace your variables with some positive numbers and see, are these truly equal? So now be careful, right? This whole thing is the numerator, so I'm going to put that in parentheses. In parentheses, 200 times, and then a to the half. I said let a be 3, so 3 to the half. Right, so that's the numerator. And then divided by, and then the denominator. I'll put in parentheses. This whole thing's a denominator. It's just one factor though. B to the 2/3. So 7. I said B was right, 7 to the 2/3. And hopefully, if we did things correctly, this will give me the same exact number as I got up there. Look at that, 94.6655428.6. They are the same. And that should happen no matter what you plug in for A and B, as long as they're positive numbers, it looks like. All right, they said assume all the variables are positive in these. So plug in 10 for A and 15 for B and do the same thing down here. You're going to get the same numbers back. They should be equal all the time. And again, try that out with all your other examples with variables too, and you'll see that hey, these are indeed equal all the time. They represent the same values all the time. Great. So lots of properties there, right? So you got a lot to learn. When you have that product property, quotient property, power to a power, fraction to a power, that any non-zero number to the 0 power is 1. Lots of things, lots of properties. All right. And also too, there are more than one way to do these usually, right? The way I just did this, probably the best way. I don't really see too much more to do on that one, but you saw in a lot of the other examples that you could have approached them in some other way and still gotten the same result. Just depends on what order you decide to use the properties in. All right. As I like to say at the end of these videos, do the best you can to learn the material on your own before you go looking for help. I find that when people take the time and effort to learn material on their own, they remember it better and for longer. I'm more proud of it. So read the material, of course. Read the author's examples. Perhaps even try to work out the solutions to some of the author's examples before you look at what the author did, and see if you can learn from some mistakes there. Obviously, work on plenty of practice problems and exercises, and check solutions whenever they're made available to you. See how you're doing. And of course, don't just give up after the first attempt at a problem, first approach. As you've seen from even this video, there are very often several approaches to a problem that'll work out. So if after several attempts, several approaches at a problem, you're still not getting it, perhaps you should try to read the material again. Maybe even a third time, more slowly, more deliberately. Take notes. And if you've worked on some problems, you probably also have a better idea as to what the author wants from you. So then you'll know what better to look for in the reading. So reading that second or third time, you might see some things that didn't pop out at you the first time through, and it'll make it that much easier to remember. But if after that, if after several read-throughs of the material and several attempts at problems, you're still not getting it, you're still not feeling it, clicking, well, then it's not a sign of weakness whatsoever to go out looking for help. That is what other people are there for. So ask a teacher, a tutor, a friend, someone who is in your class who knows the material well, and is willing to help. Look for supplemental materials online. There's tons of that out there. Look for videos online. There's loads of them too, like this one, or plenty of other ones out there better than this one. I assure you, you can find them easily. But just keep at it. Stay persistent. Keep practicing. Don't give up. And I think the hardest part too is to try to stay positive about the subject. You'd be amazed at the difference a little tweak in your attitude toward a subject can make. Think to yourself, believe to yourself that you're going to enjoy it, that you're going to be excited by it, you're going to use it. And it's amazing the difference it makes. It really is a little tweak in your mindset, a change in attitude toward a subject. All right, so stay persistent, keep practicing, stay positive, don't give up, and I just know you can get it. And thank you very much for watching.